The purpose of this video demonstration is to help first responders recognize electrical hazards. This video is for informational purposes only and is not intended as training. Only DTE Energy qualified electrical workers are authorized to work on DTE Energy's electrical equipment. All others should maintain a minimum 20-foot distance from downed power lines and anything they're touching at all times.
Welcome to the Arcs and Sparks demonstration. Let's take a look at the objectives we are going to cover in this presentation.
In this Arcs and Sparks demonstration, we will identify the dangers associated with downed electrical wires, identify appropriate distance to or from a damaged or downed wire and anything it is touching, recall how electricity travels and what materials act as conductors, recall what step potential is and how to safely remove yourself from potential danger. And finally, recall appropriate guidelines for using Danger Live wire tape to secure a 20-foot perimeter around a damaged or downed wire and anything it is touching.
Hi, I'm Chris Fleming here from DTE Energy. I'm a lineman for the company going on 25 years this year. I'd like to welcome you here today to show you our Arcs and Sparks demonstration. What we have today here is a transformer, and we're going to be able to take and show you and how to take and produce 4,800 volts on the top side. This is a controlled environment. We're going to be dealing with only 1 to 2 amps, upwards to 3 amps maximum. Out in the real world, there's thousands of amps on our power lines. My partner is Chuck Dortenzio, and he's my switchman, and he will be overseeing the safety of me, being that safety is number one to us here at DTE Energy.
Hello, like Chris said, my name is Chuck Dortenzio, and I'm also a lineman for the DTE Energy. I'll be working with Chris as an assistant here, helping to make sure this program goes along as safely as possible. My current position now at DTE is the safety director for Local 17.
You probably wonder how we're going to be able to take and produce such a high voltage in a small arena here. We're taking a transformer and taking 120 and 240 volts on the secondary side of the transformer, and we're going to be able to produce 4,800 volts on the top side. What we're doing essentially is backfeeding this transformer. We like to talk about this especially because this is what could happen during one of our storms or a normal day-to-day operation out there. In a wire down situation, whether it's primary or secondary, if things are still intact and going to the transformer, if a customer fires up a generator out there, that generator could produce the same type of voltage what we normally do on a primary side. They could take that 120, 240 volts, take it out their overhead service and find this overhead transformer and produce that same high voltage. Also, if they have an underground service, they could go out and find that first green transformer sitting in their backyards and produce that high voltage out there and get back to our overhead lines. It poses a great problem not only for us as employees but also public out there too. You probably wonder how we handle this. Out there, us as linemen, we wear rubber gloves. Our rubber gloves are rated at 19,000 volts. And we take these gloves and we take and capture air in them every day. We make sure that they're in good condition. At 90-day intervals, we take these gloves and they get sent down to Warren Service Center. They wash them, and after they wash them, they stick a probe inside of the glove, and they put 19,000 volts in there, and they're measuring for any transient voltage on the outside. After they get done with that, and if it passes a test, they put it onto a pump. They pump it up to about 2 to 3 times its normal size. And at this point, they're looking for yellow. And you may ask why. This is being a BY glove, a black-yellow glove. They're looking for the yellow to see if there's any types of cracks or abrasions in the glove. We also have BYB gloves, which are black, yellow, black. And in that, we have 80% yellow compressed from 20% black on inside and outside of these gloves. Chuck and I both have checked our gloves today. They're in good shape, and we're going to get started here. The arc's going to get quite bright, so you might not want to look directly at it for the audience in here. We also wear a pair of rubber sleeves. Our sleeves are rated the same as our rubber gloves. These sleeves were invented and they were brought into play because of the injuries that were happening to linemen out there from the elbow to the shoulder. Also, I'm going to put on my safety glasses. We also have a pair of dielectric overshoes. These overshoes that I have on here are just a secondary point of precaution. And we also have our proper PPE, FR clothing on a pants and our shirt, which are HRC 2 or greater. All right, Chuck, we're going to take it fired up here and see what's going on.
Coming on.
Does it look any different? Does it smell any different? No, it doesn't. The only thing that's different on here is we have a little light that's on here. It's a set of testing lights. And that's to allow for Chuck and I to know that we have our unit actually energized. On our meter, it's showing how much voltage? 4,800 volts. So we're not telling you anything different than what I said that we're going to produce out here. But as you can see, it looks no different, it smells no different, and those are the wires that we're mostly concerned with. Those wires that are down and not doing anything out there are the most dangerous. The ones that are arcing and sparking, we know to stay away from them. The ones that are not arcing and sparking, sometimes you may infringe upon that 20-foot rule. Don't ever get closer than 20 feet from any down wire or anything that wire is touching. If you're putting up wire down tape, be sure you're also maintaining that 20-foot perimeter. How many people think electricity can jump? Anybody think it can jump out there?
Yes.
Okay. How far do you think it can jump?
A couple of feet, maybe?
A couple feet? Is it jumping across here 2 feet? No. How about down to a foot? No. How about down to 6 inches? No. How did we all get here today? Drove here, right? And inside our car, we've got what? Spark plugs. And in those spark plugs, it's about a 32nd of an inch. At this low voltage, what we consider on our primary of 4,800 volts, it's about a 32nd of an inch, the same it is as a spark plug, that the electricity will jump across. What happens, though, is the people out there believe that electricity jumped out and grabbed them, but what happened is they already had made contact, and when they pulled away, it gives them an illusion that that electricity jumped out 8, 10, 12 feet at them. But the contact was made. Go ahead, Chuck. Talked about the different PPE that we're wearing. The hard hats that are made out there and what we wear on any construction site has a dielectric value. It means it resists the flow of electricity.
No.
As you can see on the outside of the hard hat, nothing's going and tracking across there. It's very important that if you adhere anything to your hard hat, it has to be something that's non-conductive. So any sticker, if you put anything on there, has to be non-conductive. We also work in the great state of Michigan where the temperature could be 90 degrees and it also could be 20 below out there. With these hard hat liners that we wear out there, even though they're FR rated, you have to be careful. When your sweat or any type of gel or anything that you put on your hair becomes a great conductor of electricity, as you can see, that voltage will track right across it. So make sure that you always have your PPE on properly. Us as linemen out there, we wear a special pair of boots, a pair of line boots out there. They're in the neighborhood of $250 to $600 a pair for our line boots out there. The boots that we wear have a special arch in them for when we're climbing up and down those poles out there and that too. But there's no foot product out there that we can rely on to take and keep us safe. The only thing that we can wear is our rubber gloves and sleeves. I'm going to show you here, nice leather upper, neoprene sole on here, but with a little bit of contamination of water. Go ahead, Chuck. You can see that that voltage is going to travel across. What we can't figure out yet, though, is the manufacturers of our line boots. Some of them still use nails or screws on the bottom to hold our heels on. We as linemen out there wear a dielectric, or it's considered a dry weather overshoe, not only protect us from the moisture and the contamination that's on the ground, but here again, we can't rely on nothing on our feet because it can't be tested. The only thing that's proven to test is our rubber gloves and sleeves. The fire departments out there and the police departments, they're usually the ones that are the first ones called. If an accident scene happens, 911's being called either by the pedestrians or people who are next to it, or if there's a wire that comes down in the backyard in the middle of the night, usually 911's called. Our fire departments that are strategically placed out in the communities, first ones on the scene. Firemen have to use a lot of precaution when they're entering the backyards because when they enter those backyards, they don't know what they're getting into. So they have to be able to identify and see what they have. The boots that they wear are not dielectrically tested either because the smallest pinhole in the bottom of the boot, as you can see here in a second, is what could happen. Go ahead. At 4,800 volts could travel right through a small pinhole. Might not let any water in their boot, but it definitely is going to find that electricity out there. Go ahead, Chuck. Ropes and lines. We use a lot of ropes and lines here at DTE Energy. We have barrier ropes that we use out there. If you're ever at one of our substations, or if you ever have to get inside of the station, if you see an orange barrier rope, mean that there's an electrical hazard on the other side. Treat this like a brick wall. It's no different than our yellow barrier tape when it's positioned at 20 feet out and beyond. You can't cross it, can't go under it, can't pass anything through it because there's an electrical hazard on the other side. But use caution around the orange barrier rope if you ever do see it on our property. The other ropes and lines, you probably may ask or wonder, well, how we get all of our equipment up and down the tops of those poles. It's a hand line. A hand line that we use is a pulley mechanism that we tie everything on to get up top of the pole and to the bottom of the pole. It also is our lifeline. If something was to happen to Chuck or myself at the top of the pole, we're the only ones that can rescue each other. There's no EMT, there's no fire department, there's no policeman that's going to go up there and get one of us down. We have a special way. We're qualified and tested every year on pole top rescue, and we make sure that we take good care of our ropes. But ropes become contaminated. All of our rope that we use is probably some of the best rope that money can buy. But without any type of insulated break, whether we're using a link or a hot stick with it, you have to remember that the contamination that you put on there just from your hand or the dirt and debris from the ground out there can cause electricity to travel through. I'll show you the power of 4800 volts. Go ahead, Chuck. As you can see, it's going to travel all the way through that rope. You might look at it and say, oh, that don't look like much. But it only takes the amount of energy to stop or to light up a small nightlight to stop a human's heart. I'm going to show you the power of 4800 volts. It's actually going to burn this rope in half. Any one of those arcs, go ahead, Chuck, or any one of those sparks, or any bit of that moisture you see through there is definitely enough to do a lot of damage to your body. So don't use any ropes, don't use any shovels, don't use anything to move those down power lines. Keep the public safe and keep people back by putting your wire down tape up. I'm going to go through the Mylar real quick first, okay? We also have other things, that debris that gets up in the tops of our poles out there. Mylar is one of the biggest issues that we do have if it comes in contact with our power lines. It comes in many forms. It comes in granola bars, comes in Three Musketeer bars, comes in potato chip bags, but it also comes in the balloons. The balloons out there, when people have parties, they see them with the kids today, they always want to go out, and after they get done with the party, they want to see how far those balloons can take and fly. But for us as linemen and us as a utility, they're a dangerous situation if they become entangled into our power lines. If we have to go up there and actually remove it down, we have to use a lot of caution. Remember, we're dealing with 3 amps here, very small in a controlled environment. Like I said before, upwards of hundreds of thousands of amps on our power lines. This balloon, go ahead, Chuck, is just floating along, and if it comes in contact, it's instantaneous, the fire that you could have up there. Okay, Chuck.
Sorry.
Okay. Does anybody know the #1 cause of our outages out there?
Down trees and tree branches?
Down trees and tree branches could be about 2/3 of our outages per year. We spend millions of dollars a year trimming trees out there. We trim our trees to the National Arborist Code out there, not only to take and provide safety to the public, but it also to provide electrical service to our customers. If we don't maintain that clearance out there, the outages would be even greater. You got to remember, when a storm blows through, or even a nice day, if something was to come in contact and it goes up into the actual power lines, it's about 3 to 5 seconds when a branch comes down. Here it's going to take a little bit longer because we're in a controlled environment.
Come on.
Go ahead. I'm going to speed it up a little bit and get it kind of close. But that 3 to 5 seconds, that voltage is tracking across the outside of that branch, and it's creating something that's called carbon residue. And once that residue, go ahead, Chuck, is built up across that branch, electricity will flow very easily. I got a piece of one of our old wood cross arms here. It's been in our box here for about, probably 8 to 10 years. I'm going to show you on the outside of this piece of cross arm, that electricity will track across here.
Coming up.
Go ahead. It's hard to see inside the building here, but I can feel the vibration and the tracking in my gloves. But nothing like the carbon residue on the other side of the actual arm. Now once that path is established, you'll see the voltage travel right across. We also like to take and talk not only to our employees but the public if we're doing this demonstration out there. If you ever have a power tool, if you have an appliance or any type of carbon residue that's on the side of your wall or next to those boxes, the electrical box there, shut the power source off to it, clean that area up very well, and make sure there's no carbon residue because it's a good place for fire to take and come. What happens a lot of times when those storms blow through and our power lines do come down, they come on top in the backyards, and usually in the backyards or the front yards or along the street, there's fences. And with these fences being connected, and wherever that wire's at down on that fence is considered a high voltage situation. High voltage to us is anything that's 600 volts or more. If I was to come in contact with that fence, it's going to blow me back. It's going to do some serious damage to my hands and my feet where it enters the next to my body. If that's not bad enough, all these fences or garages or anything that's attached to that fence, somewhere down the line, you're going to see a low voltage situation, 600 volts or less. If I was to grab a hold of that fence or come in contact at that point, it's going to make my muscles constrict. I'm going to have a hard time getting off of that fence unless somebody was to actually cut that wire. So use a lot of caution out there. If you don't have the proper PPE, keep the distance that you need at all times from the down wires. What this is similar to is something that's called step potential. Where that wire's down, a high voltage situation exists. At that high voltage situation is like throwing a rock on a pond. When that rock hits the pond, that source of the high voltage is right there. But each ripple outside, as you see on that pond, is a different voltage source where it gets to that low voltage. If you're walking into that step potential situation from your front foot to your rear foot, what you're going to feel is a difference in the voltage between the two. If you feel that or see that, don't go down to all fours. The best thing to do is to stay on your feet and just shuffle out of the area. Okay.
Coming out.
Things with fences out there, anything that's attached to that fence becomes energized. Anybody think that it's hot down low here or energized down below here? Sure enough. Could be Uncle Louie's tomato plant, could be a grapevine. Anything that's attached there, you can see that that 4800 volts is traveling right across there. All along the fence. How about our wire?
No.
How come that electricity is not traveling on that wire?
Because it's attached to an insulator.
It's tied into the insulator on there, and that's what we keep our electricity at bay, to keeping that voltage traveling down those poles out there. This is the smallest style insulator that we have in our system on our primary voltage, and it handles up to 4800 volts. The bigger the insulator, the higher the voltage. The smaller the insulator, the lower the voltage. But any place that we touch on here, even on our wire, you can see that voltage is traveling across. Check. Okay, we've done a lot of talking. As you can see, we're still going through here. We just got a couple more demonstrations just to show you. We've done all of our demonstrations so far with our gloves on. We're going to need a volunteer here in a second, but I want to make sure that the glove's in good shape. So we're going to take and put this glove on here. We've got a little bit of moisture. You can see the water dripping off some of our stuff, whether it was the boots or the gloves here. And with it dripping off there, it kind of simulates what happens to us. If we're on a hot, humid day and we're out there and we're sweating, our gloves get moisture inside of them on the outside of our body also. If it's a rainy day, this is what happens to us when we're up there working in a high voltage situation. So we want to make sure it's a good glove. We get them from our lab down there before we get our volunteer. Go ahead, Chuck. Going to check it, make sure it is. We see a little snapping and cracking on the back side of this glove, but it's a good glove. Okay, Chuck. So we're going to get our volunteer. Chuck's going to take his gloves off. Make sure he doesn't create no problems with it. Get a volunteer from our audience there.
Just want you to compromise this glove in the thumb right here, all right? Just one little pinhole all the way through, okay? Be careful. Thank you very much.
All the way through, Chuck? All
No,
the way
sir.
through? Okay. Want to take that out of there?
Yep.
Okay, so now we got a glove here, and we just showed you that it was a good glove, but it's got a hole in it now. And this glove's kind of like a bicycle tire, right? If you were a kid out there and you were riding your bike at the time, if your bike had a small pinhole in the tire, you're going to go very far? Probably not, right? You're going to have a flat tire till you can get it fixed. A lineman out there, if we were to work with our PPE and not have our PPE in proper condition and good working order, we're not going to go very far. That hole is small enough in there. If we were to fill this glove full of water, it'd probably be a slow or small drip out of it. We capture air in our glove, and if we ever think that we compromise our glove, we stop and we make sure that it's a good shape before we proceed with our work out there. So we got a small hole in here. Nobody wants to use this glove, right? Very, very smart audience we've got here. So we bring our own volunteer. You might have seen him before. His name's Oscar. He's part of the Myers family. Usually comes in families of 8 out there, right? But Oscar's too flimsy to take and simulate your finger because he doesn't have a bone. So we're going to use this number 2 piece of copper and simulate a bone and slide old Oscar on here. If I can put him up there. Kind of looks more like your fingernail, a little bit more rigid. He's got a bone in there. And Oscar's got a skin in our body. We've got skin on our fingers also. And inside our body, we've got what? We've got blood vessels, muscles, tendons, salt and saline solutions. Those are all great conductors of electricity. So we're going to put old Oscar, he's going to go in our glove, our apprentice here, he's going to go to work. And the first thing that our apprentice didn't do was what? He didn't check his glove. He didn't make sure that his PPE, his proper safety gear was in good working order, or he didn't realize that he compromised that glove, and there's a small hole in there without his knowledge of it. Does anybody know how fast electricity travels?
Faster than the speed of light.
Speed of light. It's about 186,280 miles per second, almost 7 times around the world. I know I can't outrun electricity, and we have to make sure that we wear all of our safety gear like we do every day, and that's how we can control the product that we produce out there. Go ahead, Chuck.
Come on.
Because if not, and if you have a small pinhole in there and you don't realize what you've got, this is what the potential could happen. Perfectly good glove until we put that small pinhole in there. Any place that I touch, on that glove, you can see the electricity's traveling through it. Okay, Chuck. I'm going to get out of my PPE. Got everything unhooked there, sir?
Yes, sir.
All right. We're going to be able to show you what could happen if we don't follow the rules. Because with electricity, the burn or the accident usually goes in very small, but it's going to come out quite large on the other side there. With electricity, it burns from the inside out. If we don't wear the proper rubber gloves or the proper PPE out there, that's what could happen to you. You may look at Oscar and say, how's he touching them? Remember, with that electricity burning from the inside out, he's not very hot on the outside, but on the inside, that cooking is going on. So with that, we'd like you to take and remember 3 important rules here at DTE. The 20-foot rule. Anytime that you see an electrical source or energy, high voltage or low voltage, and a wire down tape, it's 20 feet at a minimum out there. Proper PPE, whether it's the FR clothing that we wear, whether it's our safety glasses or our hard hat, us especially as linemen, when we're trained and qualified electrical workers in high voltage rubber gloves and sleeves, we have to have them on if we're in that mad distance out there at all times. And at DTE Energy, our number 1 goal is safety at all times. Thank you.
Let's review what we covered in this Arcs and Sparks demonstration. We were able to identify the dangers associated with downed electrical wires, identify appropriate distance to or from a damaged or downed wire and anything it is touching, recall how electricity travels and what materials act as conductors, recall what step potential is and how to safely remove yourself from potential danger, and finally, Recall appropriate guidelines for using Danger Live wire tape to secure a 20-foot perimeter around a damaged or downed wire and anything it is touching.